Okay.
Okay, thank you.
Let me make sure everyone else knows. Oh, Sophia already sent something.
Okay, right. There we go. There you go. I just need to switch my camera real quick. Oh no. All right. Okay. Okay. Welcome everybody. Welcome to the exam 4 review session. Hope you guys are ready to tackle the exam. And if not, then that's what we're here for. If you have any particular questions, anything you still feel a little bit iffy on, we're here to help. So I guess what we can do is, do you guys have any questions already? Do you guys have any questions?
So, lattice energy, I'm still not entirely sure how to go about with that.
All right. Are you having trouble with the concept? Are you having trouble with, like, for example,
so like with the atomic radius and lattice energy, more so, that's what really I'm being a little more confused on. For question 4 in the homework, right, it says of module 13, it says of the following solids which would have the greatest lattice energy and why. Sodium fluoride, cesium fluoride, sodium chloride, sodium bromide, and sodium iodide. Trying to compare those two, all of them together, right? I found out I did it wrong, so I'm not entirely sure how to just to decide which lattice energy was greatest, right? Because atomic radius and lattice energy is kind of confusing to me still a little.
All right. Okay. So let's go over with that one then. So there's a paragraph in your module 13 if you guys haven't seen it. It's a little bit of a doozy because it's 2 giant paragraphs, and it can seem a little bit daunting to read if you guys aren't used to like reading. But it actually tells, so something that it says in there is that when the lattice energy of ionic compounds increases as the ionic charge increases. So the larger your charge is, regardless if it's a large positive or a large negative charge, what matters is that it's like very large. Like, for example, +1 or -1 is going to be smaller than like +2 or -2. These are going to be larger, even if they're positive or negative. This is what they mean by like larger charges. So as ionic charge increases, lattice energy also increases. So lattice energy, who can, do you guys have an understanding of what lattice energy actually is? Or do you have an idea more or less what it is?
It's the energy that's inside of the atom itself with, depending on how many electrons it surrounds, right? Or?
Not quite.
Okay.
Not quite. Any other ideas, guys? What's a lattice? What do they mean by a lattice?
Oh, okay. So it's the energy that has the energy of the strength of the attraction between the anion and cation.
Right. So what happens with a lot of these with ionic compounds is that they don't make a molecule per se. Well, they can do, but like they don't make exactly a molecule. They make like a little kind of like a whole lattice that with the attraction between them. I don't know if maybe you guys have seen like that. You guys have seen pictures of what ionic bonds look like when they have these when you have these little crystals of ionic compounds. That's why you don't say that, oh, ionic compounds make molecules. They don't make molecules. They make like these little lattices amongst themselves with the electrostatic attraction between themselves. So that creates that lattice energy. And in this case, the bigger the ionic charge in those ionic bonds, the larger the lattice energy will be. Another thing that also contributes to lattice energy being larger is the radius size. So the smaller the radius is, the smaller the radius of the ions, regardless if it's the cation, both the cation and the anion, the larger the lattice energy will also be. So the ion with the smallest ionic radius will also have the largest lattice energy. So those are two factors. Ionic, small ionic radius. Bigger, lattice energy. Actually, I probably should draw an arrow going up. So the first thing that you guys should focus on is the charge. Whether the charges are going to be bigger first, and then you guys are going to figure out if the ionic radius is going to be smaller, right? So let's look at, for example, that question that Sebastian brought up. What are I think there were 5 of them?
Yes, it was sodium fluoride, cesium fluoride, sodium chloride, sodium bromide, and sodium iodide.
Sodium bromide and sodium iodide. Right, cool. Okay, out of all these guys, do you see any difference in the ionic charge between them? What's the charge on sodium?
Sodium's +1.
Sodium is +1, right? So that applies for pretty much all of them except for cesium. What's the charge on cesium?
It's also +1.
+1. All right. What are the charges on fluoride?
-3, right? No, is it
Fluoride?
negative? It's -1.
-1. Actually, you guys notice something. What do all these elements have in common?
They're all in the same group.
They're all in the same group. So what's the charge on that specific group?
-1.
-1. So all these are going to have a -1. Is there a huge difference in like the charge? Do they have any differences in their charges?
Nope.
No. All right. So that's the first thing that we see. There's not really any difference. So we're going to go on to the next thing. The smaller ionic radius. Between them, among the metals, which ones have the smallest ionic radius? Sodium or cesium?
Cesium.
Which ones have the smallest ionic radius?
Oh, wait.
Somebody said something, but I think I missed it.
Is it cesium?
Cesium? What do you guys think? You guys saw your ionic radius trends in module 12.
Sodium?
Sodium, right? Sodium is going to be smaller than cesium. So we can automatically disregard this one. This one's not going to be, this one's not going to have the largest lattice energy because cesium is a lot larger than sodium. So we can already disregard that one. And you can actually look it up too, like look up ionic radiuses. You guys might see that there's a huge difference. All right. So so there's not really any difference between the sodiums because we have sodium in all of these. What should we look at next? What should we look at next?
The anions.
The anions, right? So we're gonna look at the differences between the anions, which you guys might notice are actually bigger, are actually a lot more different. Which one of these is gonna have the smallest ionic radius?
Fluorine.
Fluorine, right? Fluorine is gonna have the smallest radius. So what does that mean for sodium fluoride?
It has the smallest
Smallest.
lattice energy.
What do we say about the small radius? Small ionic radius, what does that mean?
Oh, smaller ionic radius, the energy increases.
Right, exactly. Oops. Great. So this is going to have the highest lattice energy. This has the smallest, and these have the smallest ionic radii in their anions. Does that make sense? Or actually, peer leaders can actually correct me if I'm wrong.
No, yeah, it's all good. Yeah.
All right. Okay. So you got so for lattice energy, if you guys have to see that, if you guys by chance see this in your exam, you guys might you guys see this in your homework at the very least. But if you do see it in your exam, the larger lattice energy will be determined by one, the largest ionic charge. So if you have a +2, then if you have +2 or -2 in there, then you should probably have a larger ionic radius. Oh, actually, another thing that happens with the charges is that you can multiply the charges of the anion and the cation, and that will help you find out which one is going to have the largest lattice energy as well with the ionic charge. Right. So, for example, you would multiply for sodium, you would multiply +1 times -1 for fluorine, and you have a -1. You get -1. That's just a way to find out whether or not you have a large lattice energy based on your ionic charges. But that would be useful for other problems.
Not in this case, since they're all -1, right?
Yeah. So for this one, it wouldn't be much of a difference because they're all -1. Yeah, exactly. So the next step, if ionic charge is like the same for all of these, the next step is to find out which one has the smaller ionic radii for both of these, for both the cation and the anion.
All right.
All right. Okay. So any other questions, guys? Okay. Okay. So I think what we can do is we can look at questions from the review, from the unit core review. And we can just go ahead and answer these questions. Right. Unless the peer leaders have a different idea. Andre, Brooke?
Well, Well, does anybody still like before we could do the review just to make sure? Does anybody have any questions though? Oh, I think you already asked that, huh? Yeah, I don't think anybody said.
Well, we could, and if you guys have any other questions from the homeworks that you guys haven't still kind of have trouble with, we can also go through that too.
Yeah.
Yeah. And if at any point that we're doing the Unit 4 review, any of you guys want to like stop and kind of go deeper into a certain topic, like, oh, I just realized I need a lot of help with Lewis structures, just let us know and we can do a bunch of examples if that helps you guys.
Yeah, definitely.
So, yeah, basically.
All right. Okay, so let's go. I'm gonna go ahead and erase it, and don't worry, it should be in the. I'm recording, so it should be in the video, hopefully, in the recording. All right. So let's go over. Hope everybody has your workbooks. Unit 4 review. The first question is asking if reactivity increases due to effective nuclear charge in groups. So I'm just gonna write it out. Oops. I'm gonna write it out because I feel like this one's an important one. Reactivity increases due to effective nuclear charge. Which of the following elements will react most violently with water? Okay, so we have A, B, C, D, and D is all of the above. All react the same. Lithium, potassium, and cesium all react the same. Okay. All right, reactivity increases due to effective nuclear charge. So what is the effective nuclear charge, guys? What's the effective nuclear charge? What's in the nucleus, guys?
Sorry, is it the protons? The
The
amount of
proton.
protons?
Yeah, there's the protons. Right. So what's the charge of, so what is the charge of the protons? By extension, what is the charge in the nucleus?
Positive.
Positive, right? So you have your protons in here. And what happens when you add more protons to it? What happens when you're adding more protons?
Does it become nuclear?
Well, it doesn't become nuclear. I mean, what happens to the charge of the nucleus as you add more protons?
It becomes more positive.
Becomes more positive, right? So your effective nuclear charge is nuclear charge is the
Positive.
positive, right? So you become more positive. So if you become more positive, you're able to pull more electrons, right? So reactivity increases due to the effective nuclear charge, right? According to this question, which of the following elements will react most violently with water? Which one of these three is going to have an larger effective nuclear charge?
Would it be cesium?
Would be cesium. Why?
Because it has more protons in it.
More protons, and it has a larger effective nuclear charge compared to lithium and potassium. So the answer would be cesium. Well, at least that's the answer that's given here. And actually, we can. It is. You can see videos. They're like these really fun videos. I really recommend that you watch them because they're super entertaining. Where people would they throw group 1 elements like lithium, sodium, potassium, rubidium into like pools, little pools of water, and they fizz like the lithium, sodium, they fizz like crazy, like they're like very, very reactive. And as you go to potassium and rubidium, they even start exploding in the water, and it's like really, really. I think that's a really good way to show how reactive these elements are. So it's gonna. It also shows like why cesium would be very, very reactive. All right. Does that make sense, guys? All right. You good? Okay. Let's go with the second question then. Which of the listed elements and ions are isoelectronic? So before we actually do get these, I'm gonna go ahead and write these down. First, Al plus 3. As I'm writing these down, could somebody tell me what the word isoelectronic means?
Isoelectronic would mean to be having the same amount of electrons as a noble gas, or the next nearest.
Yeah, they could be. They have the same amount of electrons. It doesn't necessarily have to be the same ones as a noble gas. It just means that you have the same amount of electrons. As if you're an ion, you have you're isoelectronic with some other element. You could be isoelectronic with some other element. Okay, 3 plus. Then you have B, Kr, B1, and C 3 plus. All right, this is where I hope you guys remember your electron configurations. So let's go ahead and work these out. We want to find out which one of these are isoelectronic with each other. So the way we can find these out is, how do we find these out? How do we find out if these are isoelectronic to each other or not?
Subtract the electrons from, or subtract the charge from the normal charge of the element.
Well, yes, but also what else do we need to do? We need to write out.
Check if they have the same electrons.
They have the same electrons. So how do we find out if they have the same electrons? What do we write out?
You gotta write the electronic configuration for all of them.
There you go. There you go. You gotta write that configuration to figure out if they actually do have the same amount of electrons. Okay, guys. So how about you guys give me the configuration for aluminum? Actually, I'm gonna give you guys a few. How about you guys take a moment to write all these down, and you guys can let me know what these are. All right. Just take a moment so you guys can do it. Okay. Okay. Who's got the configuration for aluminum +3?
That would be 1s2, 2s2, 2p6.
2p6. All right. Oh yeah, that's right. Okay. What about argon, guys? Actually, just for simplicity, because some of these do get pretty long, how about you guys try to give me the abbreviated one, the one with the noble gas core. For example, for aluminum, that would be neon. Oh, well, no, well, 1s2. 2s2. All right, for argon, what's the configuration for argon? What do you guys got?
Do you want it in
Actually, give me whichever one you guys want. Either way is fine.
1s2, 2s2, 2p6, 3s2, and then 3p6.
All right. Okay. What about neon? Oops.
Mm-hmm. 1s2, 2s2, 2p6.
So 2p6. Right. Give me yttrium. Yttrium. It's this one, by the way.
Abbreviated krypton.
Okay. How about you guys give me the configuration for that one? Instead, like the.
So you want the configuration for yttrium, right?
It's like abbreviated krypton. Yeah.
Okay. For krypton, right, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p6.
There you go. Excuse my shoddy handwriting today. I don't have my my trusty stylus today. All right, for scandium. For scandium +3.
Excuse me, abbreviated argon.
Okay. So it's got the configuration of argon, which we already found out here. Okay. So then I guess it's easier now to find out which ones are going to have the same configuration, right? Which ones are isoelectronic with aluminum +3?
Neon.
Neon. All right. There any other ones that are isoelectronic with aluminum +3 and neon?
No.
All right. Which ones? So isoelectronic with argon.
Scandium +3.
Scandium +3. And for yttrium +3, we saw that krypton has that configuration. Okay. Do you guys have any questions? Do you guys need the clarification on this one?
I think it's just better like to write out the whole thing and then just cancel like the last electrons and then you see which ones they match. I mean, that's what I do.
Right. Yeah, right, exactly. So we can just check this one in case maybe it wasn't. Maybe you're like, is it really just krypton abbreviated? Let's see.
No, you're good. I'm just like, for me, it was just easier to write out the whole thing.
But yeah, it is easy. It is easy to do that. That's how we find out which ones are isoelectronic or not. Or if we do have like if we have, for example, the configuration of like the abbreviated configuration of the ground state element, we can just, like you said, take away electrons, and then we can see which ones are isoelectronic or not. Okay. So what's the answer for this question? So which one has our answer that we found?
B.
B, right? So the answer for this one is B. Okay. Let's go over with the next question. And clear these drawings. It says it can be concluded that atoms increase in atomic radius going down the group in the periodic table. Can be concluded that atoms increase in atomic radius going down the group in the periodic table, and the energy needed to ionize the element will decrease. Which of the reactions is the most endothermic? Okay, so as I write these, I'm going to write out the answers, and in the meantime, how about you guys tell me what does endothermic mean?
Endothermic is a process in which the heat is gained in the transformation.
Okay. What's another way we can think about endothermic reactions? We're gaining heat, but we're gaining heat, right? Yeah, we are gaining heat, but something else. But we can heat is a type of what?
Energy.
Energy, right? So you can think of endothermic reactions as a gain of energy. So this means that we need to put in energy into these reactions so that we're able to ionize them. All right? Do you guys get it? Like this. Which ones need the most energy so that we can remove that one electron from them? Okay. With that food for thought, which one? Think about it. Which one is going to need the most energy? If atoms increase in that atomic radius, as they increase in atomic radius, the energy needed to ionize the element will decrease. Which one of these is going to need the least amount, the most? Which one's going to be the most endothermic? The one that needs the most energy?
Lithium?
Lithium, because it's
smaller.
It's the smallest. The smallest one is going to need the most energy to remove its electron. All right.
According to for that one, it's saying that the answer is B though in the answer key.
I don't know if the answer key is correct. I was just checking on
Yeah, that's why I was saying it could be wrong. Like for example, the first one, I wasn't super sure if it was cesium. I think it should be cesium, but some of these review answer keys are wrong. Unfortunately, we haven't gotten around to actually fix them. But there might be a different reasoning, but you know, we're going to consider this to be lithium, and we can actually look up the ionization energies for these, and we could compare whether lithium or sodium have the most energy. All right. Okay. Okay. So we got a next question. Do you guys, Brooke, Andre, do you guys want to continue with the next question, or are you guys okay with me going over this one?
I could do that one if you want.
Okay.
So
Asking please.
what's up? Okay, for sure. Thank you. Okay, so okay, there you go. So number 4 is kind of like a module 13. So we could do this many ways, honestly. If you guys wanted to, you could write out the electron configuration for all 4 of these things. Well, you might have to actually, yeah. So it says which of the following compounds will generally contain 1 lone pair, 3 sigma bonds, and no pi bonds. So the reason why I say that you wouldn't have to draw them is because I would recommend practicing so much that you'll see some of these Lewis dot structures and you already know what they contain. You know what I mean? Like I know some because I've written like ammonia and ammonium. I've written them so many times. Their electron configuration. I mean, they're Lewis dot structures that I already know what they consist of. You know what I mean? So this is what I mean by practice, because it'll make problems easier. Like you'll spend less time. You know. But let's go one by one. So what does it mean by lone pair? So it's saying 1 lone pair. What is that? What is 1 lone pair?
The 2 dots that don't have anything bonding to them.
2 dots. So let's put the 2 dots right there. It's gonna have 1 lone pair, 3 sigma bonds and no pi bonds. What does sigma bonds mean? So 3 of them. What are those gonna be?
It's a single bond, right?
Yeah, sigma bonds are single bonds. So yeah, so we know we're gonna have 3. So and it says no pi bonds. Remember, pi bonds are just these or this. Remember, like, and it says it has none of them though. So we know that at least a double bond has 1 pi bond, and then the triple bonds have a like 2 pi bonds, I think, if I remember correctly. So we know that it has none. So I'm not even gonna consider. I know that I'm not gonna have double bonds, triple bonds at all. It's all gonna be single bonded, and it's 3 of them. Okay. So I know my element should look something like this or like this. It doesn't really matter how you want to draw it. You just, oh shoot, I'm already kind of writing the answer. So yeah, you're gonna kind of want it like this. You know, it's kind of, see, this is what I mean. Like I already got ahead of myself, but let's write them out. Okay. So let's do the first one. What is that one called? NO3 negative. Can anybody remind me what that's called, just to make sure you guys are good on your module 2 knowledge?
Nitrate.
Nitrate, right? Exactly, nitrate. All right, so this kind of, I'll kind of extend this problem. I'll make it a little longer just by also recapping on Lewis dot structures, right? Okay, so let's do nitrate. So does anybody have a method they like to do for Lewis dot? Because I know there's many ways you can start this. So does anybody have a set one that they like to do that they find pretty easy? If not, I can do my own one.
Starting out with the elements, then creating the bonds, and then going back in and filling over the missing pairs.
Okay, so which one's going to be our central atom in this case, actually?
Nitrogen.
Nitrogen, right? So the way you figure out what your central atom is just by seeing between these two which one is least electronegative. Okay? And just a couple rules. Hydrogen can never be your central atom, and yeah, that's the only rule, I think. Okay, so let's make nitrogen, and we know we're gonna have 3 oxygens around it. So what I recommend you guys do, because I used to do this one thing that would cause me to make so many mistakes when I took Chem 1 and when I was doing Lewis dot structures. I used to do it like this. I used to write out my valence electrons right away, and I would try to connect everything from there. But I would realize that would kind of lead me to make a lot of mistakes because I would make wrong bonds and all that. So what I recommend you guys do is just count up how many electrons you need to use, okay? So the way you do that is you just add up valence electrons and any charges, okay? So how many valence electrons does nitrogen have?
Nitrogen has 5 valence electrons.
Awesome, yeah. And what about oxygen?
That's 6 valence electrons.
Exactly, right? And so there's 3 of them, so I need to do all of those valence electrons times 3, right? All right, and we need one more thing. So remember, whenever there's a charge, that just means that you have 1 more electron. Okay, it's a charge of -1, so you're adding an electron. So let's add the 1 right there. So how many electrons do we have in total? So that should be 18 plus the 5 is 23, 24, right? All right, 24. So I know I have to use 24. So instead of me doing the valence electrons like on each one, let me just make it easier and let's just say we have to solve everything that has an octet rule. Or let me make bonds also. You can either do that or you can make bonds because you know that nitrogen can make at least 3 bonds. So you know that it's good doing this, right? And you know that each oxygen has to be bonded, right? So how many electrons have we used up there for starters?
6 electrons.
6, right? Because there's 2 in every bond. So 2, 4, 6, okay? So 24 minus 6, how many do we have left?
18.
18, right? Exactly. Okay, so 18 left and just, well, let's fill out our octet rules. Well, I know that oxygen for sure has to follow the octet rule and so does nitrogen, but let's do the oxygens first. So if I try to fill out the octets on each one, let's see what we get. So if I filled out the octets in every single one, what do I get? Well, how many electrons did I use up? I'm sorry.
You've used up 18.
18, right? So 18. So so we had 18 left and we used up 18. So can we use any more?
Yep.
No, right? But so do you guys think we're done here? No, right? Why aren't we done? Why is this? Well, you could look at me. You're like, wait a minute. Well, I used up all my electrons already. I can't add any more. I can't. So why is it wrong?
Nitrogen is also part of the octet rule, but it's missing 2 electrons.
Exactly right, but I can't add anymore because we've already used all of them up. So I can't put any two. I can't put a lone pair. I can't do anything. So what can I do to make nitrogen fill out the octet rule?
Double bond.
Double bond, right? So, and the cool thing about this is you can make lone pairs into bonds, right? So another way that you might see these drawn, if you look them up on Google, you could see that lone pairs are sometimes drawn like this, right? You'll see them as little lines. So yeah, you can visualize it like that. So if you see them online like this, they're both right. They both mean the same thing because just a little line just means 2 electrons. Okay, so let's do that. Let me use another color. So let's say I want to move this one over here. Well, I turn that into a bond, and then now I erase the bond that we had here, right? So now that I did that, well, is nitrogen following the octet rule now? Is this oxygen, the one that I moved the bond to, that I moved the electron pairs, is still following the octet rule? Yeah, right. I just made a little double bond to fill out the nitrogen, right? So let's do this one then. So we've used up all of our electrons. So nitrogen has no lone pairs, right? So do you guys think this is the one that's being described in your question? No, right? And they should have been, I think it should have been a little more specific. Just they should have mentioned like the central atom should have had all those things because I assume that it's a central atom. Okay, so this one doesn't fill it out anyways, right? How do you know this right away?
Nitrogen doesn't have a lone pair, and also there's double bonds.
Yeah, there's double bonds, right? And that means that there's a pi bond at least somewhere there. So we can knock this out as our answer. Okay, so let's do NH3. So how do I draw that one? It's Lewis dot structure. So this one's a compound, so it's kind of easy. It's easier to do because it's not an ion. So let's get started on this one. How many valence electrons does nitrogen have again?
5.
And how many does hydrogen have?
1, but in this case it's 3 because there's 3 hydrogens. Exactly.
So I multiply it. So, and there's no, remember, ammonia, which is NH3, is a stable compound. It doesn't have a charge. It has covalent bonds, so it doesn't need to do anything. So we don't add any electrons or take any. So it'd be 8 in total, okay? So let's do that. So we're gonna make nitrogen our central atom because remember it's the fact that even though that hydrogen is less electronegative than nitrogen, hydrogen can never be a central atom anyway. So that's why we still make nitrogen our central atom. So I'll put 3 hydrogens around it. And remember, right away, well, I know that hydrogen can only make one bond, so I can do that right away. I can do like one, and one to each. So how many electrons have I used up right now?
6.
6, right? So I have 2 left. Well, I know that it's not necessary to make double bonds, and even if I wanted to, I couldn't, right? Because I mean, hydrogen can only make one bond. So those 2 electrons, I can put them up here so that nitrogen can have its octet filled out, right? Because now it does. So it's like 2 and then 4 and 6 and 8, right? So nitrogen's all good. And we used up 8 electrons already, so we're fine, right? What about this one? Does this one follow the guidelines that were given? Yeah, right. 1 lone pair, okay. 3 sigma bonds and no pi bonds, right? So, I mean, we could already assume that this is our answer, but you could do the rest to figure it out, okay? So let's have ammonia still drawn out. So this was NH3, right? So remember, you're adding just 1 more hydrogen, right? So let's put a hydrogen up here. So in ammonia, it looks like this, but you have a hydrogen now. You're going to make ammonium. Well, remember, hydrogen can only make 1 bond, so it can only attach itself to one of these. So let's say it attaches itself to one of these. Well, what do you think has to happen to that little electron that was there? The one that's kind of alone now. It kind of has to go away, right? Like it's got to be removed because nitrogen can only have an octet filled out. This isn't, if I keep it like this, it isn't an octet anymore. It's 9. So I got to remove that one. So what happens when you remove an electron? How have we been writing so far ever since module 2 that we state that we've lost an electron?
With a positive sign.
With a positive sign, right? So that tells us that we've lost, but we need a number now. So how many electrons did we lose?
The 1.
1, right? So that's why usually NH4 is NH4 plus 1. That's why ammonia is NH4 plus 1. So does this one fill out the requirements that are stated there? No, right? Because this is 4 sigma bonds. It does have 0 pi bonds. It doesn't have any pi bonds, but it doesn't have any lone pairs either. So it can't be ammonium. Yeah, ammonium, sorry. NH4. All right. So far, I mean, we're being proven right that ammonia is our answer. So you could, and let's do that last one out. What is that one called? ClO3. What is that Lewis-Dot structure? I mean, what is the name of that compound?
Chlorate?
Chlorine?
Chlorate.
Oh, chlorate. Yeah, exactly. It is chlorate. So remember, guys, if you still are having trouble with this, with the naming of these, I recommend that I highly recommend that you study on module 2, if that's still throwing you off. So yeah, this one's chlorate. So it's an ion. So we know that these are going to be one of our trickier ones, but the good thing is we already have a method as to how to solve it, right? So let's see if that method still works out. How many valence electrons does chlorine have?
7.
7, right? And oxygen has 6. There's 3 of them. And what's it called? We have 1 electron because of the negative charge, right? So 7 plus 18 plus 1. What did you guys get for that?
26.
26, all right. So we can only use 26 electrons. So let's see. So let's write chlorine here, and then 3 oxygens, okay? So what I like to do is I like to make a single bond right away because you know that each oxygen has to be at least bonded once. Some of them may have double, triple, you never know, but each one has to be at least bonded once. So how many electrons have we used up here?
6.
6, right? So 26 minus 6, we have 20 left. So my next step, what I would recommend is to figure out what has to have its octet rule filled out. So in this case, it would be
Oxygen.
Oxygen, right? So yeah. So let me fill that out. So let me fill out the octet rule for oxygen. So, all right, so I filled it out. So how many electrons do I have left up there?
You'd have 2 electrons left, right?
Yeah, because I used up 18, right? Six on each oxygen. So I have 2 left. So I can't do anything right now to the oxygens because they have their octet rule filled out. So what about chlorine? Chlorine doesn't necessarily have to follow the octet rule, but it can still, it's okay with having 8, right? So right now it has 6. So let's put those last 2 in there. So I'll put it as a lone pair. Okay. So now let's see. Well, I mean, we used up, so we can count our electrons. It's 8 right here, 16, 24, and 26, right? So I've used up all my electrons. My octet rule is filled out, but is this my right answer? No, right? Well, it isn't. So, but you're like, wait a minute. Well, we did all the requirements. Yes, we did, and technically this isn't terribly wrong, but it's not the preferred one. So, and what I tell my students is that chemistry's been around for so long that we already have our standards, what we like to use. And even though this is in a sense not wrong, it's not the preferred way. So we have to do something else. So why is this not the preferred way?
Because there's multiple lone pairs.
No, well, it's not necessarily that case. It's so this is where you dive in deeper to module 13 as something known as formal charge. So what does formal charge have to do with any of this? Does anybody know? So formal charge just in a sense is it helps us find out which is our best Lewis dot structure. So even though this is a correct Lewis dot structure, it's not the best, definitely not. It's for sure not the best. The reason why is, well, let's figure out what the formal charge is. Well, formal charge, you just figure it out by comparing electrons, okay? So you have a huge equation on page 230 or 270 something, I think. If anybody would be as kindness to just say the page for the whole class, because I can't find it right now. But it's around page, it's on module 13. It has a big title that says formal charge. And there's a huge equation that I really don't like to memorize. I don't recommend memorizing. It's a lot of unnecessary work. But so what I like to do is just, for sure, you do need to keep the first part of the equation maybe. So chlorine,
Right.
I'm sorry.
I can go ahead and step in with that one. With that equation, I know it.
Well, okay.
So there are 2 ways to do it. The way that I like to remember it and the way that I've shown my students, of course, you don't have to do it, is I like to the formal charge I like to calculate with first valence electrons minus the number of bonds around the atom that you're calculating the valence the formal charge for, minus the number of electrons in lone pairs. So this means that it's not the number of lone pairs, it's the number of electrons that are in lone pairs around the atom. So that's the way I like to memorize it. There's one that instead of being by the number of bonds, it's half of bonded electrons, which is basically the same thing. The bonded electrons, you know that in one bond you have 2 electrons and you have half of it. That's the way that's the number that you're gonna use. Minus, I can't remember which one was that. That one was actually but sometimes they use this one instead of number of bonds. I'll have to find out the other one, but I'll write it. Keep going, Andre. Sorry, I just wanted to interject on that.
No, you're fine. So, well, I couldn't say the equation because like I said, I didn't memorize them. So I was gonna say the little method I do is because I find them. I did used to use the equation, but then just someone showed me this way, and I was like, oh, well, that makes it a little bit simpler. But like I said, memorizing equation also would be is also a perfect way to do the problem. Okay. So what I do is I like to make a little box around whatever central atom I'm looking at. So like we're looking at chlorine right now because that's what we prefer to look at for Lewis dot structures. So I like to make a little box. Okay, a box that splits up every bond. Okay, so and at the end of every bond, hopefully you guys know that at the end of each bond is an electron, right? So there's an electron here and an electron here and an electron there. And if you notice, I mean, what we're doing here is exactly the same thing that Corina was saying. Yeah, so it's perfect if you memorize it either way, whatever suits you best. But you'll notice that we're doing the exact same thing. So it's perfectly fine whichever way you like to do it. Okay, so I like to do just the valence electrons, which we already figured out, which is 7, right? Minus the electrons that are inside the box. So how many electrons are inside the box with chlorine?
5.
5.
5, right? Because, yeah, 1, 2, 3, and then 2 right here. So 5, yeah, 5. So that's how we figure out the formal charge. So 7 minus 5, because remember, 7 was the valence electrons minus the 5 inside the box. Well, we get positive 2. So this is the reason why this Lewis dot structure doesn't really work, because we prefer this, the formal charge. So I'll write FC for formal charge. We prefer to have this, if it can be 0, great. If not, we want it as close as it can be to 0, okay? So the way we can get it closer to 0 is by adding more electrons inside that little box, right? So what can we do to put more electrons inside that box?
You'll need a double bond.
Exactly, a double bond. So let's make one just to move a little slower. So, or not slower, but just to be a little bit more careful. So I'll move this bond right here. It doesn't matter what bond you want to move. I'll just move it right there. So, okay, so I made one double bond. Let's see if that works out. I'll make the box again. So remember, it's still 7 because it's still 7. Chlorine has 7 valence electrons. That's a general rule. Well, how many are inside the box now?
6.
6, right? So does that give us so that gives us 1. So can we get to 0 though, or do we have to stop at 1? Because remember, we haven't increased any amount of electrons. We haven't added or subtracted any. We still have the same amount. We're just manipulating the bonds a little. So can I manipulate another bond?
Yeah, you can.
Let's see. Because yeah, and remember, does chlorine have to follow the octet rule? No, right? So this is why it's completely fine that I added that it has more. So right now it has like 2, 4, 6, 8, 10. It has 10, but that's fine because chlorine can take it. Chlorine doesn't have to follow the rule. So let's make another double bond. So let's say I want to move this one right here. So I move that one from that oxygen and I erase the one that I just moved. So let's make another box. So now how many are there inside the box?
Now there's 7.
Now there's 7, right? So 7 minus 7 is 0. Are we satisfied? Yeah, right. We finally got the central atom. Remember, why I'm doing chlorine is because it's a central atom. That's the reason why I focused on chlorine so much, because you always got to have the central atom to have a formal charge of 0 to find the best Lewis dot structure, or 0 or whatever's closest to 0, okay? That's why we like to have that as the, so yeah, this is why this is our preferred Lewis dot structure. So usually if you look up, even though the one we just did had a bunch of single bonds, it's like I said, it's not wrong, but it's not the best one. Therefore, it kind of makes it wrong, even though it's, yeah, it's a tricky thing. But yeah, this is our preferred Lewis dot structure for chlorine, or chlorate, sorry. But even then, I know that was a little like super off topic, but it was all connecting everything else. So you still got kind of like a little module 13 lesson in there. But when answering the question, does it satisfy whatever it was asking? So no, right? Because look at chlorine. Chlorine has, okay, yeah, it has 1 lone pair, but it only has 1 sigma bond, and it has like a bunch of pi bonds, which we don't want at all, any. So what was our answer again at the end?
The ammonia.
Ammonia, right? NH3 would be our answer. Because even though we proved that it was right a while ago, remember, I don't know about you guys, but I'm always unsure. I don't like to find my, if I find my answer that I think is it right away, I still like to check the other ones. So I recommend you do that as well. depending on how much time you have. Also, that is very important. Manage your time. If you're confident, maybe you can kind of already guess which problems you don't need a lot of time on and all of that. Okay, but yeah, ammonia should have been your answer. I know it says it's nitrate, but no, like I said, yeah, for some reason there's a bunch of questions wrong in this key. So yeah, it's for sure ammonia though, because I mean we just went over it and it made sense, right? So all right, I'll finish up with that one. I think Brooke, if you have any problem you want to go over, or does anybody like want Brooke to go over any specific module or anything, or just any questions?
Yeah, what do y'all want help on? Is it the drawing? Is it the geometry? Is it the configuration?
Hybridization, all that.
That's another one.
It's
Any of
okay
that
to say
really?
all of them.
Yeah.
All of the above. Okay. Let me see if I can find a question. How about let's try number 7? Because that one looks like it has a molecular and electronic geometry, and I want to see if I know that shows up a lot on Professor Noveron's exam. So let's try doing that one.
Oh, that one's a great one. I like it. I like this one.
I like all of them. I'm just a nerd.
I
Okay.
like this one because it forces you to draw it, and it tests you on whether you know your molecular and electron geometry.
All right. So it says consider the structure for a sulfate ion. Which one best describes the molecular geometry? So let's start with what is the formula for a sulfate ion?
SO4 negative.
SO4 negative. Everyone agree? Yes, no?
-2.
-2. Good, yeah. If you remember, this is where we're kind of like circling, making full circle with chemistry. You have to think about stuff that you just learned and all the way back to module 2 with those polyatomic ions. Awesome. So that's our formula. And now let's start to draw it. So first thing we should focus on is what will our central atom be?
Sulfur.
Sulfur. Let me draw that. Awesome. Cool. So now we are going to surround this with all of our oxygens, right? So currently we're going to do this. And let's see, is this the best configuration of sulfate that we can do? Let me fill in the valence electrons. Is this the best way to draw sulfate?
No. No.
Yeah, be confident with your answer. Don't worry if it's right or wrong. Yeah. So what's the problem with this so far?
That it doesn't have enough electrons in it, right?
Enough?
Or it has too many electrons?
It's something with the electrons, right? So, and like Andre and Corina have mentioned, there's about a bajillion ways you can draw things, you can calculate formal charge, all that. I personally really like to work with formal charge just because it always gives me the best answer. So I'm gonna go ahead and real quickly, like let's look at the oxygens, right? Because all these are the same. So what's the current formal charge of this one oxygen?
-1.
-1, right? Because the way I do it is valence electrons minus the lines minus your dots. So we have 6 valence minus 1 line minus 1, 2, 3, 4, 5, 6. 6 dots, which gave us -1. Perfect. So this oxygen has a -1. This oxygen has a -1. This oxygen has a -1. And this oxygen has a -1. Yeah? Let's look at sulfur real quick. What's the formal charge on sulfur?
-1. Right? Or is it positive? +1.
I love the confidence though. Some people are like, I don't know, could be this, could be that. I'd rather like someone be like, not really, than just be like, well, I don't know. Yeah. So let's try calculating it for sulfur. So what's the valence electrons for sulfur?
6.
6. Yes. Minus the lines it's connected to. Oh, that's a
4.
terrible box. I'm so sorry. Yeah, 4. Minus the lone pairs it has, or the dots.
0.
0. Perfect. So it's currently at a
2.
2 charge. Awesome. So this is our current sulfate. If you notice, that's a lot of weird charges. Yeah? We got so many negative ones. We got a +2 in there. And remember, just like Andre said, it strives to be as close to 0 as it can. So what is going to happen is we're going to try and see if we can balance out some of these charges. So just taking a look at this, what do you think we can do to get rid of some of these charges?
Oh, you can double bond two of the oxygens to sulfur, and that brings sulfur down to 0.
Perfect, yeah. So, like you said, you gotta double bond something, right? And lucky for us, sulfur doesn't follow your octet rule, right? It can have more than 8 electrons sharing with it. So, let's bond 2 of these oxygens. So let's bond this one, and let's bond this one, because he told us that we're gonna need to bond 2. So now, what's the formal charge of this oxygen atom?
0.
0, right? Because it has 6 valence minus 2 lines minus 4 dots. Do that math, you get 0. So now we're looking at an oxygen with a formal charge of 0. This is 0 and this is 0. And now let's take a back look at that sulfur, because when we double bonded it, we not only affected the oxygen, but the sulfur as well. So looking at this, what's its formal charge?
0.
Good. We had 6 valence minus, it now has 6 lines, and no, so it's 0. Yay. So, looking at this, we have a 0, a 0, a 0, and 2 negative ones. So this is going to give our overall charge of -2. And if we take a look back at that formula, we wanted an overall charge of -2, right? When you draw it out, make sure you always remember to include your charge somehow or some way. Yeah? Feeling good? Cool. So this is how we draw sulfur. Or the sulfate ion, my bad. Now let's take a look at how to find its molecular geometry. So what 3 things do you need to look at when you're talking about any kind of geometry, molecular or electronic?
Bonded region, the lone pairs, and the magic number.
Perfect, yay! Yeah, is that those first 3 columns? You have your magic number, and then depending on that, you're going to have some bonded and some lone pairs. So when talking about the magic number, what are we talking about exactly?
The area around the central atom.
Yeah, what's special about these areas? I'm looking for a specific word.
The electron region.
Yes, good. Those electron regions. You might hear them be called densities or whatever. It all means the same thing. Where on this atom can you find those electrons? So, looking at the sulfate ion, my first question should be, what atom are we looking at in this whole molecule to find this magic number?
Sulfate. Sulfur. My bad.
So far, yeah. It's okay. We all know now. Yeah, no, we're looking at sulfur. It's our central atom. So, we're looking at this sulfur. And how many regions can I find electrons? How many bonded regions do we have?
4.
4. Good. We have 1, we have 2, we have 3, we have 4. So our magic number is 4. How many of those 4 are bonded and how many are lone pairs?
All 4 are bonded.
Beautiful. All 4 of these are bonded and we have no lone pairs. Yay. So based off this information, the 4, 4, and 0, you can take a look at the chart that you have and you can just kind of follow it down. So what is our electronic geometry?
Tetrahedral.
Good. Tetrahedral. And now what is our molecular geometry?
Tetrahedral as well.
Yay! Tetrahedral as well. So, out of all of the answer choices you have, which one is your answer?
D.
D. Woohoo. Yay! So that's really what these kinds of questions are. I know he loves to put these kinds of questions in there, like what's the geometry of this molecule? So it's really almost entirely based on how well you can draw molecules. Yeah? Great. Cool. So do y'all have any other questions you want to go over? Any other types of questions?
Maybe hybridization, or however you say it.
Yeah, hybridization. Let me take a look.
There is one for 15, which also combines polarity, and there's also 19.
Okay, cool.
So 15 and 19.
Awesome. Let's try 15. So I'm gonna clear this. Goodbye. Awesome. So looking at number 15, it says nitrogen gas was reacted with hydrogen gas to form ammonia. What type of hybrid orbital is used in ammonia, and is there an overall dipole moment? Awesome. So, who can give me the formula for ammonia?
NH3.
Yes, NH3. Perfect. So, like always, how do we draw this out? What should our central atom be?
Nitrogen is the central atom.
Perfect. We have nitrogen. And then, how is it going to look? Where am I going to put those hydrogens?
3 sides around the nitrogen.
Okay. Cool. So are these all single bonded, or do we have any double bonds, or
They're all single bonded.
all single bonded, right? Cool. Is this the form for ammonia?
Nope, you're missing a lone pair.
Perfect. Yeah, remember, you got to make sure, because this molecule has a formal charge of 0, you have to make sure. And so far, when looking at this nitrogen, he has 5 valence electrons minus 3 lines minus no dots. So he's currently at a +2. So to get rid of it, we have to put a lone pair on him. Boop, boop. And I like to group mine like that. Cool. So is this the structure for ammonia?
Yep.
Yes, right? And just like Andre and Karina have said, once you practice these kinds of problems enough, you're going to know all of these molecules, not because you really know how to draw them, but because you practice them so much. So you're going to become like freaking Super Saiyan at drawing molecules. It's going to be awesome. Yay. Okay, so now we have to figure out what type of hybridization we got. So, how do we determine hybridization?
Looking at the electronic configuration.
You can. There's a little bit easier way. We just talked about it.
Oh.
Does have to do with electrons, so you're close.
Not the formal charge, right?
No, you're close.
Close.
You're like, you're getting warmer.
Man.
Anyone else now? I feel like Sebastian's the only one who's like been talking.
Come on, guys, don't be shy. Don't let Sebastian speak for you guys.
I know, Sebastian's currently the only one who's gonna ace his exam.
Oh, valence electrons, right? Or am I missing the mark on that still?
The thing is, yeah, all of those could be yes. I'm looking for one specific thing.
Well,
Really
actually,
close.
there's a much simpler way to do it. I don't know if Brooke, you were going to talk about it.
Yeah.
It's all right. I guess, does everybody give up, or does anybody remember how to have an idea how to do it? How to do it? Sebastian's already waving a white flag. He's literally waving. Oh my gosh. All right, let's see. I'm going to show you a little trick. I know not every single one of you is going into, well, some of you guys might go into Chem too, so this will be useful to you guys. And you guys will be a Super Saiyan, like the one on the corner. You guys will be like Super Saiyans, just like Brooke said. All right.
He's got some like fire.
Yeah, you're missing. Thank you. All right. So there's a way. There's an easy way to do it. I like to think of it as counting. And I'm not gonna erase anything. So there's a way I like to do it. 1 electron region, that's S. 2 electron regions, sp2, sp. 3 electron regions, sp3. Oh, sorry, sp2. What's next? What's the next logical one?
SP4.
All right, is it? No,
Or is it SP3D?
that's it. That's sp3 because I actually made a mistake and said sp3 before this one, but this one should be sp2. All right. Okay, so that's the easy way to do it. It's kind of like counting, right? So then the configuration for this one is, what's the configuration?
SP3.
sp3. So how about maybe we practice a little bit on these just so you guys can understand what I mean by like counting.
Yeah. I have another way that I do it. It's literally the same thing though.
Oh, okay. Yeah, I think maybe we can, I'm just gonna draw these and you can show us your way, Brooke.
Awesome. So I'm gonna do it for water. I don't know. Let me see. Let's do green. I don't know. Feeling environmentally friendly today. So just like Corina said, it's a lot of counting. And if you notice, the way I do it is she counted 1 electron region per orbital, right? Or hybridizated orbital. So it's based on like that magic number that you use when you do electronic and molecular geometry, right? So we said that this guy has a magic number of 4, right? Because he has 4 densities. So let's take a look at water. We have 2 lone pairs and 2 bonded pairs. So what is its magic number?
4.
4, good. We have 4. And now the way that I do this, and it's literally the same thing as Corina, but I like to draw out how many orbitals it could take up versus how many orbitals it does. So for example, I know that the S orbital can only hold 2 electrons and it has that one, like, if you remember those orbital diagram boxes, yeah, it has one of those, right? There's one for S. How many are there for P in the P orbital?
Three.
6 or 3.
3, yeah. There's 3 boxes. It can hold 6 electrons. Good. So I'm going to write 3 P's. And then how many can D hold if you're going to go up to D?
5.
5. 1, 2, 3, 4, 5. So what I do is I literally write this out and then I circle which ones I need. So I'm only going to need 4 of these. So I'm going to go 1, 2, 3, 4. I'm going to use 1 S and 3 P's. So S, P to the 3rd. Yep. That's how I do it. You can use Corina's way. I don't know. Andre, do you have a different way?
I actually use exactly the one that you used, or I just do this. So I don't want to throw too many ways around because I feel like it'll just be a little overwhelming. But so for I do that same one, or I just like to look at the whatever's around the atom that you're looking at. So so like for carbon in this example, there's just you count these as one thing when you're doing hybridization, and you count it as one thing. So I just go S and then P. So I know that the carbon there is sp hybridized. But if I'm looking at the oxygen, well, I count this one again, and this one again, and I just go S, P, and P. So I know that that's SP. And how many P's were there? There were 2, so that's 2. So yeah, there's a bunch of different ways. I actually use this one, the one that you just used, Brooke. I actually like using that as well. But I've used that one. It does, but yeah, it's up to you guys, whichever makes the most
I like
sense.
those methods. Those are like real cool. I really like it. See, we're learning new things. We're learning new techniques on how to do hybridization. We're all gonna be Super Saiyans at this rate. All right, how do you guys feel about hybridization, guys?
A lot better than before, that's for sure.
Right, okay. So, the question was asking which type of hybrid orbital is used in ammonia, and is there an overall dipole moment? Is there an overall dipole moment, actually? Because the question is not over yet. We need to answer that. Is there an overall dipole moment?
No.
We got a few people say no. Anybody else have any agree? Anybody else agree? Come on, guys, don't be shy. All right. What do we need to have an overall dipole moment? What do we need to have a dipole moment? Anybody have any ideas?
Double bond?
The what?
Double bond?
Not quite. Well, the bond has a little bit to do with it. It has to do more with what elements are bonded to each other. It doesn't have to be a double, triple, or it doesn't matter if it's a single, double, or triple bond. It matters what the elements are are.
So then it would be no, because there's 3 hydrogens bonding to 1 nitrogen, right?
Well, think about it. The dipole moment. So the dipole moment is what, if there is a dipole moment overall, like there's nothing canceling out that dipole moment, that means you have a polar molecule. So how do you start having a polar molecule? How do you start figuring out if you have a polar molecule or not? Starts with an E. E.
Electronegativity?
Electronegativity, exactly. All right, exactly right. So specifically the electronegativity of, well, in this case, we want to find out the electronegativity, which I hope you guys remember is how strongly an element pulls electrons to itself in a bond. Because especially in covalent bonds where they're sharing electrons, but they won't necessarily share them equally. So in the case of nitrogen, what's gonna happen with the electrons that it's sharing with, at least, let's say this hydrogen, for instance. What's going to happen to those electrons? Which one, is there going to be an equal pull between the nitrogen and the hydrogen?
No.
No, right? Which one's going to be the more electronegative element? Nitrogen or hydrogen?
Nitrogen.
Nitrogen, right? It's the more electronegative, it's going to pull the electrons closer to itself. And that difference in electronegativity is going to cause a dipole moment or a polar bond. And this is a polar bond because it creates a dipole moment. What's going to happen with the other three hydrogens? What's happening between those bonds? What's happening between the nitrogen and this hydrogen?
The same thing.
Same thing. What's happening with the other hydrogen and the nitrogen?
Same thing.
Same thing. So they're pulling towards, so the nitrogen is pulling the hydrogens towards itself. So think of these dipole, these arrows, these are the vectors that represent the dipole moment. So what happens with vectors? If any of you guys are familiar with physics, for example, physics uses a lot of vectors. What happens with these vectors? Well, what do you guys think? Well, actually, I'm going to rephrase this question. I'm going to change the question, actually. What's happening is there an overall dipole moment? If you add up or cancel, in a way, if you add up or cancel these arrows that you have, are they canceling out? Are they adding up?
They're adding up, right?
Yeah, they're kind of like adding up. They're all going upwards. I think the only way they would be canceling out is, like, for example, this one and this one. They're going in similar directions, similar opposing directions, but overall they're going off. They're all going up. So what is the overall dipole moment, if any, if there is a dipole moment, an overall dipole moment? Where is it pointing up?
Pointing towards nitrogen.
Yeah, it's pointing up. So this would be your overall dipole moment. The partially negative charge is going towards the nitrogen. The partially positive charge is on the side of the hydrogens. Okay. So which one of our of the four answers that were given is the correct answer then? Got it.
Would it be A?
It's A, right? It's A. Our answer is going to be A. Well, that's an alpha, but A. Same thing. Okay, any questions, guys? Concerns? Complaints?
No, I just have, I feel like we need more practice, especially, just couple, we have some homework. If you guys could explain some of them, that'll be great.
Oh, if you have the question ready?
Yes, I have one. Selenium, SeCl2.
Okay, I'm gonna go ahead and clear the drawing. Is that okay?
Yes, it's on page 298.
Page 298. Could Brooke or Andre, could you guys help me with that one? SeCl2.
Yes.
What question is this?
So it's asking for the structure and like the magic number, the electronic geometry, the molecular geometry, the band angle on the central atom, and the hybridization.
Okay.
Of the central atom.
Okay, magic number.
All of them.
Page 289, you said? Or 298?
298.
Yeah.
Okay. Structure, magic number. Okay, I got it. Okay, I know this one. Electronic magic number, electronic geometry, molecular geometry, bond angle, and hybridization. Okay. Okay, guys. How about, so let's try drawing SeCl2. What's the first thing that we need to do when drawing a Lewis structure? Before drawing anything, what's the first thing that we gotta do?
Count up all the electrons.
Count up all the electrons, exactly. So how many valence electrons on selenium?
6.
6. How many valence electrons on the chlorines?
7.
7. We got 2 of them. So how many valence electrons do we have available?
20.
20. 20. Boom. All right. So we're gonna go ahead and draw it. Which one is gonna go? Which is gonna be our central atom?
Selenium.
Selenium, because one, it's gonna be the one that we have the least of, and also it happens to be the least electronegative one, so it's the best candidate, right? And we can draw. What's the next thing that we're gonna do?
Bond it with chlorine.
On the chlorine, draw that skeleton. I like to say that this part is drawing the skeleton, which is just connecting the terminal atoms with the central atom. All right. What's the next thing that we're gonna do?
Fill in the remaining electrons.
Right. Okay. So we already used up 4 of them, 2 for each bond. So we got 16 remaining electrons. Where are we going to put those remaining electrons? Maybe we should probably fill up somebody's octets. What are we going to fill up those octets for?
For sulfur?
We don't have sulfur here.
I mean selenium.
For selenium. Well, selenium can have an expanded octet, so we're not sure if they need to fill up their octet. But what about chlorine? What about chlorine? What about chlorine?
Yes?
Yeah, we can fill up their octet. So how do we fill up their octet? What are we going to draw?
The dots.
How many?
2 on each
6.
side of the.
6. All right. 2, 3, 4, 5, 6. Right? So that makes 3 lone pairs. What about the other chlorine?
6.
6. 1, 2, 3, 4, 5, 6. Okay. So I already used up 12 of them, 12 electrons. So that leaves us with 4 more electrons to use up. So we already filled up the octets for chlorine. What are we gonna do for selenium?
Plug in the remaining electrons.
How are we gonna do that? Are we gonna add them as bonds, or are we gonna add them as lone pairs?
As lone pairs.
Lone pair.
All right. 1, 2, 3. 1, 2, 3, 4. Okay. How do you guys feel about it? You guys feel all right?
Not entirely sure why the lone pairs are diagonal like that. Is it because they're all negative and you're trying to keep them away from each other?
Right. How should we draw them instead then?
I was thinking top and bottom, but
Sure. Yeah, we can do that. We can do that too. That's fine. That's fine. Don't worry. I think it's better, especially if you're drawing it that way, like kind of like a little bit linear. At least when you're doing it that way. All right. So we already got our structure ready. We got our structure. What's our magic number?
2.
2.
4.
2 or 4? Who says 2? Who votes for 2? Go ahead and use a reaction. Okay, got a few people saying 2. Anyone disagree? Somebody else said 4.
I think it's 4.
Okay. So remember the magic number counts electron regions. Electron regions involve bonds. So atoms that are bonded. Anywhere where you have bonds, and anywhere where you have lone pairs. So what is our magic number? How many electron regions do we have? 4.
4.
Right? 4. That's 1 electron region. That's 1 more electron region. That's another electron region, and then there's another one. So our magic number is going to be 4. Okay. Everybody good so far? Okay. What's the electronic geometry for selenium chloride?
Tetrahedral.
Tetrahedral. All right. What's the molecular geometry?
Bent.
Bent. Why? Why is it bent and not tetrahedral?
Because there's 2 bonded pairs and 2 lone pairs. And 2 and 2 makes bent.
Exactly. And by the way, have you guys seen the the table that's at the end of module 14, right before the worksheet, right before the homework worksheet? Okay. How does that shape look like? You guys see that shape? So I know that. So I know that for one of you guys noticed that I had drawn the electrons kind of on top of the selenium, and it looked kind of awkward in that moment. But I was kind of giving you guys a spoiler of that. But I mean, you're right. It does look a little bit awkward the way it looks right there, like kind of linear. But once you've got the geometry, it's a little. I hope it was easier to understand why I did that. But yeah, it was a bit of a spoiler. Right, we got the electronic geometry and molecular geometry down. What's the bond angle? You guys can check the bond angle in the table on the back, like at the very back of the workbook, on the cover, well, on the back cover, on the back of the back cover.
Oh, 105 degrees?
105, great. Okay, so let's put to the test the way that we learned all the ways that we learned hybridization just now. With you guys can use my way, you guys can use Brooke and Andre's way, whichever you guys prefer. So what do you guys want to do to find out the hybridization?
Count all the densities and then label them.
Okay, yeah, we can use, we already got the, right? So the densities around. So how do we label them? How do we start labeling?
You can label any one S and then the remaining 3 P.
Right, right. So you got S, P, P, and P. I think that this was Andrea's way, if I remember correctly. Or you guys can do Brooke's way as well. The way she did it was S, P, 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 D, oh, D, 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 D. So you count how many you have. You have 1, 2, 3, 4. All right. Okay, so what is our hybridization, guys?
SP3.
SP3. Okay. All right. Who was the person who was asking for this one?
Oh, it was me.
Okay. So did that help? So
Yes, it helped a lot. I just confused the magic number for lone pairs and bond pairs for some reason, so I put 2.
the way I like to, I don't really like the term magic number. That's a personal preference. I like to just use electron regions because that's more accurate.
Yeah.
And also less confusing. It's less kind of like, what's this mumbo jumbo? But once you, but that's a personal preference. You guys can use magic number. You guys can use electron regions, however you guys prefer. So, yeah. Okay. You guys have any other questions? It is. So
Can we go over problem 8 on page 300?
on page 300. All right. What? Which problem is that?
Number 8.
Brooke, Andre, could you guys help me with that one?
Yeah, it's okay, it's organic chemistry thing. It's H2N CH2 CH2 CO2H, and it's asking for the hybridization of each atom.
Wait.
And it just gives you the way Andrew's writing, it just gives you the space of the atoms, but you have to fill in the bonds.
Yeah, okay, I think that was it. Yeah, okay, so for this one, it's kind of, this is where I also recommend knowing how many bonds something can make. So for starters, carbon likes to make a certain amount of bonds. Does anybody know how many bonds carbon likes to make?
4.
4, right? So you can see all the carbon and you can already kind of fill them in, right? And it makes sense, right? Because hydrogen can only make 1 bond, so hydrogen can only make 1 bond. So you know that these two are good. So, and then you can do the same thing for this carbon over here. And then you can connect it to that carbon over there. And we'll see about the carbons over here right now, okay? We'll see about those later. So hydrogen can only make 1 bond also, right? So we can already kind of do that as well. So far, so good. So what about this hydrogen? Well, it can also only make 1 bond, right? So how many bonds does oxygen like to make? Does anybody know?
2.
2, right? So we've already made 1 out of the 2 for this oxygen. What do you think the other bond has to be?
To the carbon.
To the carbon, right? So yeah, and we'll have the 2 little lone pairs. So yeah, and you guys should start visualizing right away. Like if I drew them like this, just know that all of these, even these bonds right here, I think Corino is going over it anyway right now. These bonds are kind of pushing. Yeah, they're like magnets. Like think of like when you put 2 magnets of the same charge, they kind of, if you try to put them together, that you feel that force pushing away, but then you flip the magnet and then they stick right away, right? So So that's what's kind of happening here. And I like to think of electron pairs like these, the lone pairs, they have a little bit more force. They can push a little harder. Therefore, they're pushing this little hydrogen bond a little harder. So you can already start visualizing that this is probably going to be a little bent. And then, so that's already a hint right there of how, of what the hybridization almost, or well, not hybridization, it would be just the geometry. But okay, so we did that. We completed the Lewis dots. Oh no, we haven't completed it yet. So carbon likes to make 4 bonds, right? So how many is it missing? This carbon right here.
It's missing 2 more bonds.
Missing 2 more bonds, but luckily enough, well, what do we know about oxygen also?
Oxygen also likes to make 2 bonds.
So oxygen likes to make 2, carbon needs 2. It's a perfect match, right? So, and then again, it's gonna have 2 lone pairs. So let's check everything just to be sure. Well, what about nitrogen? Nitrogen likes to follow the octet rule, so what am I missing there?
A lone pair.
Lone pair, right? And it likes to make 3 bonds, which it already has, right? And so its octet rule is filled up. All the hydrogens like to make 1 bond, so they all clear out. Carbon likes to make 4, they all clear out. Okay, and we already did the carbon oxygen. Hydrogen oxygen, so it all makes sense, right? Is anybody confused as to how I got to this point? Maybe on this side I feel like the confusions might come from how we did over here. Is anybody confused there?
Yeah,
Oh, sorry.
I am confused.
Okay, what part confused you, or what?
Last part, the one of the CO2
COH or the
C, like the last stage, like on the drawing on the workbook was on the side bottom.
Yeah, exactly. Okay, yeah, so they have it like this, right? Yeah, it doesn't really matter. I mean, just know that in it's because what I meant was like in real life they're not just straight like lines, you know what I mean? If you were to draw this in a straight, like if you were to actually visualize this, this would be so like bent. It would look, so this is just wait until you get into Chem 2, it's organic chemistry, but just know that this is not the perfect or the best diagram to state, like to visualize these kinds of molecules, you know what I mean? Like if you were to draw this whole thing out, it would look like super bent, like it would look like a bunch of lines, and you'll probably get to see this when you take OChem, but that's a worry that you luckily do not have to worry about yet. So yeah, I'll just keep it like that for simplicity's sake. But so we did this and it all checks out, right? Well, did that answer your question kind of? So it was just a little thing that I did just because I like to help you guys visualize that this is like pushing them away, but we can keep it like this if it makes it simpler. Okay. So we did that. So let's determine the hybridization. So, and that's all it's asking for, right? Yeah, complete. Okay. Yeah. So it's all it's asking for. We already drew all the lone pairs, all the bonds. So we got to determine the hybridization for each atom. Okay. So for the hydrogens, I like to knock out all the hydrogens, right? Because they all look the same. So they'll all have pretty much the same configuration, right? I mean configuration, hybridization. So what is the hybridization for all the hydrogens? Well, I mean, yeah, you don't, yeah, it'd be, what would it be?
S.
S, right? It would just be S because they only have one thing around it, so S. And like I said, well, I don't know what method you guys like to use. Maybe you guys, I would just write S like that, and that would just, but make sure that you know that you're talking about hydrogen. That's a key thing to remember, okay? And you can also do, like I said, yeah, like I also like that way that Brooke was doing. If you just do this, well, how many things are there around hydrogen? There's only one thing, so I made one circle, so I'll make one circle here, and that's it. That's how I know it's S. So let's look at, so I know that hydrogens, they're all going to be S, all right, just by knowing that, because if you notice, they're all the same, right? So I'll just erase that for now. So let's look at nitrogen real quick. Nitrogen, how many things does it have around? So like I said, you can make circles. So 1 circle, 2 circles, 3, and 4. So 1, 2, 3, and 4. So S, and how many P's did you circle? Well, you circled all 3 of them, so it's got to be sp3. Okay? And yeah, that's one way. Like I said, it just depends on what way you like to do it. I think that that's a pretty simple, that's a pretty cool and simple way to do it. Again, you could just go S, P here, P, and P. It doesn't really matter where you start. You could have put your S over here at the left side. It doesn't really matter as long as you cover all bases. Okay, and you'll still get the same thing, sp3. So you got 3 P's, sp3 hybridized. Okay, just know that you can only have 3 P's. It can never go sp4. That's because that's not possible. So that's why you skip into D. And D you can only have, I think, 2 levels. I think that's as far as it goes in your chart. So that's what I would recommend memorizing. Okay. So what about carbon? So we know that this one's sp3. What about carbon? Does anybody want to take a guess as to what carbon would be?
sp3.
sp3 also, right? Because yeah, like I said, S, P, P, and P. So yeah, sp3. All right, so I already saw that. I mean, carbon looks pretty much the same. It also just has 4 little lines, so I can also assume that this carbon is going to be sp3. So do you guys see how, it might look intimidating, this problem at the start, but do you guys see once you solve one and you understand what you're doing, you can assume all the rest and you can be correct by assuming all the rest. So this is an sp3 hybridized carbon, sp3 hybridized carbon. And so this is where it changes though, because this carbon isn't going to be sp3 hybridized. This is because it doesn't have 4 things around it. Remember, double bonds, you don't count them as 2 things. You count them as 1 thing. And this is what we mean by magic number. I don't call it magic number. I just call them things. And by things, I just mean pairs or lines, you know? So carbon only has, well, 1 thing. And then remember, we count double bonds or even triple bonds. Even triple bonds, you count them as 1 thing. So I count this is 1 thing, this is 1 thing. So I did 3 circles. So 1, or yeah, I did 2. So 1, 2, and then 3. So this carbon is what hybridized?
sp2.
sp2, right? And then the same, you could do it again. Just remember that 1 means the same thing. So you could start your S over here. Remember 1 thing P, P, so sp2 hybridized, okay? Now let's look at the oxygen. All right, so can anybody already tell me, does anybody already feel confident enough that they already know right away what hybridization is? A carbon. I mean carbon, oxygen, sorry. Yeah, I was like, I caught myself on that.
Which oxygen?
This one, sorry.
That'd be sp2, right?
Yes, yeah, sp2, right? Yeah, because S, so remember, and also you count the things, so remember, this is what I mean by things, so like lines. Remember that these bonds, those 2 dots, they make a line, right? So you can also think of them as a line, and then remember, we count double bonds as 1 thing, so S, P, P, and yeah, and it's the same thing as that, so sp2. So yeah, that oxygen right there is sp2 hybridized. Okay, so I'll write an sp2 over here. And then let's look at this oxygen though. What would the hybridization be for this one?
sp3.
sp3? Yes, I would agree with that as well, because S and then P, P, and P, so sp3. Okay, and then the hydrogen, we already knew that it's S. So yeah, I think that was all of them, right? So that's how you do hybridization and just how you make bonds, okay? Remember, yeah, you gotta memorize what things like to make, okay? That's very important, and this is super important because you're for sure gonna see this in Chem 2, and you're for sure gonna see this in organic chemistry. You always gotta know you've gotta memorize how many bonds certain elements can make, okay? Especially these. Honestly, these are literally the whole like skeleton of organic chemistry. These are elements that you are gonna see for a long while. Oxygen, carbon, and hydrogen for sure, and even nitrogen too. So that's why I recommend for sure knowing how many bonds they can already make. So remember, oxygen likes to make 2, carbon likes to make 4, nitrogen likes to make 3 and hydrogen just likes to make 1, okay? All right, so write that down if you don't have it, because that's like a freebie for your homework. So yeah, is it okay if I erase it, or is anybody still jotting it down? Okay.
I think you're good.
All right, yeah, I think I'm good too, so I'll erase it. All right, so, oh shoot. Okay, so what, is there any other questions? Well, I just want to be also real quick. Does everybody know the difference like between electronic geometry? Says everybody gotten so far the differences between the geometries, right? I think you went over it, Corina, just, but I got distracted. But yeah, you went over it, right, already? I think you did.
I did just a little bit.
Oh, okay.
Just in case, electronic geometry, it doesn't discriminate whether you have any lone pairs or not. So it just takes into account like how many electron regions you have. So if you have 4 electron regions, if you like water, for example, like Andre is drawing right there, it just depends if you have 4 electron regions or your magic number is 4, then your electronic geometry is going to be the same, regardless of whether you have lone pairs or you have all atoms around the central atom.
Exactly. So yeah, like how I like to think of it is just so yeah, so I drew up a quick example right here. So I like to think of it as like electronic geometry is just like the quick way of classifying something, if that makes sense. Like, and I like to think of molecular geometry as the more detailed way of classifying something, if that makes sense. Because if you notice, they're all pretty much the same for electronic. It's all like, it could be, you have very few names, but then if you look at molecular, you see that there's a bunch of different names, right? Like there's more names for molecular than electronic. And I'll show you guys what I mean by that. Because look, if you look at, this is water, so H2O, and over here we have methane, which is CH4. So these are two very similar compounds, but similar in not how what they are, but like similar into how their geometry and all of that. So, but they do have slight differences that kind of helps you guys read that chart a little better. You know what I mean? So let's figure out the hybridization first, since that's what we've been looking at for the most part. So let's figure out what's the hybridization for water.
SP3.
SP3, right? Because S, so yeah, S, and then P, and P. And remember, to figure out the hybridization for the entire molecule, we're looking at the central atom. That's why, okay? So that's why water is SP3 hybridized, because we look at the central one, okay? So SP3. Well, what about methane?
It'd also be SP3.
It's also SP3, right? If you notice, it's also SP3. So this is what I mean by they can be very similar, but there's little things that you got to know what makes them different. So SP3, yeah. But, so let's look into geometry now. Well, geometry, if you look at it, it's not really the same. Because do you notice how both of these have 4 things around it, but they're shaped very differently? You know what I mean? So let me show you guys what I mean. Let's say I drew like a little cloud around this whole thing. So let's say I drew a cloud around the whole things that we marked, you know? So if I were to draw a cloud around this, do you guys see how its shape is weird? But then if I drew a shape around this, they're very different, right? But they both have 4 things around it, you know? Like that's why if you notice, and remember, what I mean by things, I also mean magic number. So, and by things, I mean this. They both have 4 things around it. So oxygen, the water has 4 things around it. The carbon has 4 things around it. So do you guys notice that? Oh, funnily enough, if you look at your chart, CH4, which is an example that they have in your little chart, if you look at the very end where it says example, CH4, find CH4 and find water. And if you find them both, you see that their magic number is both 4, right? But notice the shape though. So one of these guys is kind of like line. I like to think about it as like one of these guys may pass the first test, but then in the second test, they don't pass who they really are. You know what I mean? One of these is truly tetrahedral. One of these is just, they might seem tetrahedral, but they don't really behave in the end like a tetrahedral. That's what I mean by electronic is a little bit more vague. Molecular is much more detailed, right? So this is what I mean. So electronic, they're both tetrahedral and electronic because they both have 4 things around it. But one of them is in their molecular, one of them is a little different because they actually they're not truly tetrahedral. So does anybody know which one's the truly tetrahedral one?
Methane's tetrahedral.
Yeah, methane's tetrahedral in both cases, right? So what's water then?
Bent?
Bent, right? So yeah, and just remember, I didn't write the geometries, but just know that, well, yeah, bent would be molecular and electronic is tetrahedral, and this one's tetrahedral in both. But do you guys see what so this is what I mean by I would recommend memorizing your chart, this whole chart, but there's a difference between understanding it and memorizing it and not understanding it and memorizing it, you know? Because I feel like understanding it makes it way easier to memorize than not understanding it and memorizing it. You know what I mean? So yeah, this is what works. So I like to think just the one that for sure follows the the one that'll stay what its electronic geometry was. So like let's look at methane. Methane was tetrahedral. The way I know that it's gonna stay tetrahedral is because it actually has bonds. So those things like the magic number, I look at how many of them are actually bonds. And I know that out of those 4 the magic number 4, which it had 4 things around it, 4 are bonds. So I know that this one will stay tetrahedral. But in water, I know that 4 of those things, or only 2 of those are bonds. So I look at my chart and I'm like, okay, well, if it's 2, then it's gonna, those lone pairs are gonna kind of push it. So it'll look kind of bent, right? And then there's the last option where you could have like, let's do one more. So I'll erase it. So let's look at ammonia. Well, ammonia, if you notice, can anybody tell me right now, like they could visualize ammonia already before I even draw it? Is it similar to water and methane?
Yes.
Yeah, right, in terms of hybridization, because yeah, S, P, P, and P, so sp3 hybridized, right? So, oh shoot, we're out of time already. Give me 1 second, let me just finish this one up. So yeah, sp3 hybridized, and yeah, but do you notice how many of these are actually, so it has a magic number of what, for starters, if it was sp3? 4, right? So again, it's very similar to water, but what can we assume of its electronic geometry right away? Remember, electronic is a very vague one.
It's tetrahedral.
Tetrahedral, right? And do you guys see how, yeah, the electronic geometry, there's just like 3 tetrahedrals. So I know that it's one of the tetrahedrals, but now I got to go into my molecular geometry and find out its real identity. So how I figure that is, well, how many of those 4 that we found, like those 4 things around it, so the magic number, how many of those 4 are actually bonds?
3 of the 4.
3 of the 4, right? So I know that it's not going to be tetrahedral then, but then I remember, well, 2 is bent. So 3, well, think of 3. I like to think of 3. Well, you think of a triangle, right? Triangle has 3 points. This has this has kind of 3 points. And then this one just makes it a little bit smaller. But I know that it's 4. I know that I connected 4 things, but remember that I like to think of these as more connectable than the lone pairs. So even then, it's a mnemonic device. Like if you think 3, you can think of a triangle, and what's its actual molecular geometry? So if
Pyramidal?
You look at, what's up?
Is it pyramidal?
Yeah, exactly. And trigonal. So I like to, that's why I mentioned the 3. Triangle. So if you see 3, if 3 out of the 4 things are bonds, well, I like to think right away triangle. So trigonal. trigonal, and then just trigonal pyramidal though. Just be careful on those though, because they do mean different things like trigonal pyramidal, trigonal planar, and trigonal bipyramidal. Okay, so, but yeah, that was a little just quick thing on how to do it. Okay, so yeah, that's the way geometries work. Okay, so be sure to do examples on those. Just practice, practice, practice. I swear it'll get super easy.
Okay, guys. So we are 10 minutes over. So we're free to go. So you guys are free to go. But if you have any other questions, or maybe you have any lingering, anything lingering, please let us know. I will be stopping the recording right here. So thank you guys for coming here. Thank you for being here. I hope these 2 hours of review helped you a lot. This will be on YouTube on the Peer Leader, the Peer Leaders YouTube channel. We'll send you a link to that. I'm gonna go ahead and stop the recording, and we'll send you that. And